Hey everyone. In this video, I just wanted to go over experiment one just to make sure that everyone's on the same page here. So here I've got it opened up, and so obviously in this section, we don't need to go over it too much. Um, right, this was just looking at the bench equipment and finding the model name for all this stuff. And the front panel. The hardest thing was to, look up the thing on Google and find the user manual, which I presume that everyone is perfectly capable of doing. So a lot of these are, I think, Keysight equipment for the most part. We got one that is from Regal, the DC power supply there. But so here's an example just of the multimeter user manual. And so this can be helpful if you ever are stuck on how to do something like how to get the device into high Z mode when you're looking at the function generator and whatnot. But we don't need to talk too much about that. Um, so this guy I talked about in the example lab report. So probe attenuation. So on the scope probes, let me see if I can pull up an example. Yeah, so on a lot of these voltage scope probes, they have the ability to attenuate the signal. And so on the probes in our lab, they usually have a little switch that switches between 10 to 1 and 1 to 1. And so whenever you set the attenuation to 10 to 1, that means that as the signal goes from this probe tip through the cable back to the scope, the signal has been attenuated by 10. So if you have a 10-volt signal going in to this probe tip on the outside of this, going into the oscilloscope, you'll have a signal of 110, or sorry, 1 volt, right? So 10 volts in, you get 1 volt on the other side there. That's just one thing to keep in mind, especially when you're gathering data on the oscilloscope. You want to make sure that your probe attenuation is set up properly, and I'll try to show off how to do that at some point. So the difference between AC coupling and DC coupling. So this is something that always confuses people. AC coupling just means that we're strictly looking at the AC component of the signal, right? So we're filtering out any DC part and we're just looking at AC. So this is especially useful when you're looking just at ripple of something, or you're just interested in harmonic components of a signal. DC coupling allows you to see everything. I know that's a little confusing, but bear with it. So DC is typically 0 hertz, right? So you're allowed to see everything above 0 hertz, basically, which is, I think, the main reasoning for that terminology there. Um, so here in section two, you should find that when you measure the resistance of the cable, it's not exactly 0. And then these should be kind of review from last quarter, hopefully, just the act of measuring a resistor, and then looking at capacitor impedance. So you should know that at low frequency, the capacitor is very high impedance, and then at high frequencies, it's low impedance, just based on the impedance equation, which can be found here. Here you can see that the frequency, right, is inversely proportional to the impedance. So simulating with LT-Spice, let me quickly show you how to do this because I have fun with LT-Spice. So we are taking a resistor in the kilo ohm range. So I'm going to take that and rotate it with Control R And so to get that resistor, I just pressed R on my keyboard here and I rotated it with Control R. And then I'll press C to get my capacitor, V to get my voltage source, G to get grounds, place the grounds, W to wire, and then I'm going to phase through all this stuff here. And so to set the resistance, you can either click on this, right? So don't click on the numbered ones. These are reference designators. This is the value of the resistor. You can click on this, right click, or you can right click on the resistor itself. So in this case, I think we use 2.2 kilo ohm. And the same thing with the capacitor here. And so another thing to note is you can use these suffixes to denote, kilo ohm, milliohm, micro, and mega. So mega is MEG. So that's just one thing to keep in mind. And I think there's also pico and nano, um, and I think giga works, but we won't use any of those, I think. So for the capacitor, we'll need to right click this guy. I think we were using 0.33 mic, so you can use U for micro. Um, and then I want to say this was just a pulse. So you right click the voltage source, go to advanced, get a pulse. I don't remember exactly what this setup was, but I think this is something along the lines of this. No delay, maybe like 10 millisecond, 10 millisecond, T on, 20 millisecond, or maybe that was 10. I don't remember, but should get you a square wave here, something like that. So here we got the circuit built up, and now we need to specify what kind of simulation we're running. So we're going to be running a transient simulation um, for like 60 milliseconds. I'm not sure what it was saying to do, but there's that. And so now we've got the schematic and the waveform viewer. So in the waveform viewer, right, you want to click on these nodes in order to plot voltage, and you want to click on the devices to plot current there. So there's there's our current, here's our voltage. And so I think I specified a rise and fall time that were a little too long, maybe. So there's a little bit more what we were expecting there. So if we add the plot pane below, we drag these signals down, that looks a little bit more like what was shown in the video there. So next we have the AC simulation part. So we're going to change this guy and we're going to go to AC analysis and we're going to change the sweep to decade sweep, just 100 points per decade, somewhat arbitrarily from 1 hertz to 1 megahertz. So 1 meg. And so like I had said before, to get meg, you need to type in meg, not just M, capital M. If you type in just M, it'll register that as milli. So now we'll run this. And of course I broke it because we need to specify the AC amplitude here. And so we run this again. So I'm going to close this out, do that again. And here is the Bode plot that we're interested in. So here on the left, we can see the magnitude, and on the right, we see the phase. My intent was for you to find the -3 dB cutoff frequency, which if you zoom in here and you enable the cursor by left clicking this guy, um, this little window should pop up. And as you drag the cursor, right, so you left click and drag this around, you can see that the magnitude changes. And so unfortunately, you can't just type in a magnitude here. You have to drag the cursors, but you should be able to drag it to get -3 or somewhere thereabouts and find that your cutoff frequency is about 218 hertz. So I think that covers this part. And so here, where it says to run a transient simulation, to show that the output voltage is scaled by a factor of 1 by root 2. So if you do 1 divided by square root 2, then you get 0.707. So then if I enable the transient simulation by just right-clicking it and hitting OK, and I change this to a sine wave with a 1 volt amplitude, and then you just run it at 220 hertz. Delete these. Then you should see there's our output, here's our input. Um, and as you can see, so the peak of our input is 1 volt, and I can actually trace this and find that out there. So we got our cursor, you can see it's, 999 millivolts, which is basically 1 volt there. And then if you get another cursor and go to the peak of this waveform, you should get about 1 by square root 2, which I forgot, 0.707. So there you have it. We've confirmed through transient simulation that our output voltage is, in fact, reduced, scaled down by a factor of 1 by root 2. And so in this next step, the goal was to use equipment in the lab. And to do that, I think I'll use Tinkercad just to show you how you would set something like this up. So I'll just put it here. Actually, this is our next experiment. Let me see. And so this is a good chance to see how to use Tinkercad. So this is a Tinkercad environment. If you're unfamiliar with how to use breadboards, you can left click that guy and I think press R to rotate it if you want. And so again, we have our breadboard around this, down this column, it's all interconnected. Down this column, it's all interconnected. And down these rows, they're all interconnected. And the same with these rows. And the same here with these columns, and so on and so forth. So here, we just want to grab a resistor. So we're going to build the circuit up. And so you can press R to rotate and drop a resistor there. Um, and then I'll get my capacitor. And so you don't want to do something like this, because if we look at the schematic here, what we've done is we've basically just shorted out our capacitor, right? So it's tied to the same electric potential on both sides. So it's basically useless like that. What we want to do is make sure that both ends are tied to a different electric potential, like so. Right, so now the top side of the capacitor is up here on row 1, and the bottom is here in row 2. And so next we'll need a function generator. And I think, so you can see, I don't think it's inherently, oops, in this basic tab. Um, I don't see it there. So if you're just like looking around, you'll have to go up to here and go to all, and you should be able to find it down here in instruments. So we'll grab our function generator, and I'm going to take the positive end, right? So going back to our circuit here. So this is effectively our function generator. We want to take the positive end to the resistor, and then we're walking through the resistor to the capacitor back to ground. So the other side of the capacitor here is going to be tied to ground. And so you can just do something like that. And so we'll want to first off set our resistance. So if you left click the resistor, you want to set this to 2.2 kilo ohm. And then we'll want to set our capacitance to, I think 0.33 microfarad. And then we'll want to set our function generator to the cutoff frequency at 1 volt, no DC offset, and we'll output a sine wave. So now we've got that set up. We'll want to get our oscilloscope. And so in Tinkercad, these oscilloscopes only have one channel, unfortunately. But one thing that to note is that the oscilloscopes need to be tied to ground. And so I noticed that was a mistake that a lot of people were making, and that might be my mistake for not, informing you. But so on channel one, which I guess we'll just call this first oscilloscope here, we're just going directly to the input signal there. And then on channel two, we're going to ground. Sorry, on this negative terminal, which is our reference, we're going to ground. So this is effectively channel one. And so one thing to note is we can set our uh, vertical scale here. So if I do 1 divided by our cutoff frequency, and of course it doesn't like that, you can see that one period of our sine wave will take 4.5 milliseconds. So to get enough of our signal on here, I think 10 milliseconds would probably be a good estimate of the scale that we want to get a bunch of periods of the waveform on there. So on channel two here, right? So just like on this viewer here, so on channel one or this blue signal, we've got the input waveform, and then on channel two, we've got the output. So the input is just directly on the function generator, and the output is the voltage across the capacitor there. So we're going to look at the voltage across the capacitor. We'll take positive terminal there, negative terminal to ground. And so if we start running this, so that's not a great vertical or horizontal scale rather. So let's try maybe 5 milliseconds per division. So that's a little bit better there. Here we can see we've got a a vertical scale of 2 volts per division. So if we go up 2, 4, 5, we can see that we're up at around 5 volts, which is a little confusing there. And then here, we've got 1 volt per division. So we're up at 1, 2, 3, about 3.5. And not sure why that is. Let me pause this and troubleshoot. Okay, I'm back. So this is not the volts per division. This is actually the range from here to there. And so there are actually 10 divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which means if you take 2 divided by 10, you'll have the volts per division. So we've got uh, you know, zero point 0.2 volts. So zero point 0.2, zero point 0.4, and then 0.5. So 0.5 up to here, 0.5 down to there. That's our 1 volt amplitude sine wave there. And so actually, what I was doing here matches what we've got there. So that's good. So then on the output here, we've got a distance of 1 volt, which means that each step is worth zero point 0.1 volts, right? So we got zero point 0.1, zero point 0.2, zero point 0.3, and then we're up here at about zero point 0.5. And so that's a little bit concerning. Maybe it's actually closer to zero point 0.7, or it should be at least. So, but that's just one example, perhaps, of limitations of this simulation tool, is you can't get really good resolution. And so one thing that I guess we could do actually is try taking our period 4.5 and dividing it by 10 in order to get, just one period within this range here. So we get a little bit more resolution. So if this is zero point 0.1, zero point 0.2, zero point 0.3, this is still not what I would expect. But when you connect this up in the lab and run this experiment in the lab, you should hopefully see something closer to 0.707 like we had found here. So there's that. That's just how you do it in Tinkercad, at least. Doing it in the lab shouldn't be that much more difficult, but if it still is, we can talk about it. So in this next part, we're just looking at high pass filters. And so the idea with the high pass filter is you flip the order of the capacitor and the resistor, right? So here we're injecting a voltage, right? So our input is going straight into this resistor, and then we're feeding through the capacitor back to ground. And so if you switch the orientation of that, you'll actually get a high pass filter. And so that you can kind of see the Bode plot, or what happens as a function of frequency here. So at lower frequencies, the signal is being rejected, and then at higher frequencies, beyond some cutoff frequency, the entire signal is being transferred over. So we've got that. Diodes. Hopefully this was pretty straightforward. We can build this up real quick. So I'll just delete all this, and then we'll go with the voltage source and a diode, and we're inject 5 volts directly onto a diode here. And we'll look at the current. So I'm going to run a transient simulation for 10 milliseconds, and we'll look at this current. So here you can see the current's 3.57 teraamps, which would, explode your diode pretty instantly, probably. I think a lot of people were getting confused on finding the forward current rating in the data sheet, so we can look at that. So this is our data sheet, and I want everyone to become familiar with navigating data sheets. Obviously, it's a little difficult when you're looking at it the first time, but this first table here tells you exactly the forward current that we're looking for. So we had a blue LED. The forward current is 35 milliamps, and so that's the rating. For safe operation, you should keep the current below that. So for this next part, if we just take 80% of that forward current rating, you get 28 milliamps. Um, and then we want to find how much resistance we need. So if we have a 5-volt source and 28 milliamps, if you just take 5 divided by 0.028, you get 178 ohms in order to limit the current sufficiently. So here we have the just placing the resistor there. So if I hit R and I rotate it and I drop it here, it actually fills in the blank there. And I set the resistance to about 179 K. Or no, so actually it's not kilo ohm. And then we look at the current. Um, you can see it's well below the 28 milliamps that we want, so that's good. And actually it settles down here at 10. So let's run it for a little bit longer. Not sure why it's has this little draining profile, but it's also zoomed in a bunch. Um, so this is pretty steady around 23 milliamps there. So here we want to determine the forward bias voltage. Um, One easy way to do that actually is just to plot the voltage. So if we plot the voltage, it's 737 millivolts. But another way you could do that is determine, right? So obviously the current through here is going to be, about 25 milliamps there, 23 milliamps. So you figure out how much voltage is dropping, right? So we take 5 minus 179 times 0.023, and you get 0.833, and you subtract that from 5. Uh, well, that's not. Anyways, so I got the answer to that I found earlier in this example lab report. So let's review that real quick. Oh, sorry. So I forgot. So yeah, what we found then is actually just the voltage drop through the resistor. And then we subtract that from 5 to get to the diode there. Okay, so I think so then, to do this doing using lab equipment, so we want to build that circuit up. So, instead of this capacitor, we can just delete that guy and we'll use a LED. Um, so one thing to note is from the resistor, we're stepping into the anode of the LED. So here's the cathode, here's the anode. So we'll need to rotate this, drop it in like that. And then another thing is we're using a DC power supply. So actually, let's just delete these guys and start from this circuit. So here's our circuit. We'll want to get a power supply and we're measuring the current. So first off, we're going to set it to 5 volts. That's fine. And we want it to set the current limit to 80%. So that's going to be, I think it was 28 milliamps. And so we've got our circuit built up. We want this to be, so I had 220 ohms available. So that was the closest thing that we could use. And then we want to measure current. So to measure current, right, we're going to change this to an ammeter and we're going to step in to the ammeter. We're going to step out of the ammeter into our circuit. And then we're going to take the cathode of the LED back to ground to complete the circuit. So I think we'll be able to see that schematically here. Oh, I guess not. That's too bad. So anyways, this is the setup, right? Whenever you measure current, you're going to be connecting the ammeter in series, which means we need to step into it before entering whatever element that we're measuring current for. So we'll run this. And you can see we've got 13.5 milliamps. And actually, if we crank the voltage up, we'll hit our current limit. This guy will be close to its limit, so it'll throw a little indicator there, but we'll just keep it there. Um, so then I think if we had that 178 ohms at 5 volts, let me stop this. 178 ohms, which I think is what we have here. 179 rather. You can see we get 16.5 milliamps, which is, somewhat close to what we found here. So this default diode obviously doesn't have the exact same properties as the default diode, sorry, the LED. So keep that in mind. So here's the diode rectifier. This was the last circuit that we're building up, and actually to build this, we're just swapping the position, making sure, to keep the polarity of the diode like that with the resistor and the diode. Um, so now we're doing a 3-volt amplitude at 60 hertz. So there's that setup. We're looking at a 100 millisecond transient. That's and then the resistor we're using, the one in the kilo ohm range. So we're using the 2.2K. So if we run this, there's our output volt. That's our output current actually. So here's the input voltage, here's the output voltage. And then if we place the capacitor in parallel with the output, and we use that 0.33 micro, and you can see it reduces the ripple ever so slightly. But then the moment we have 1,000 times that capacitance, it's pretty significant reduction in the ripple. And then the last part was just measuring it um, using lab equipment. So stop this. I'll delete my setup here again. And this time, our resistor is appearing at the output. So we'll go here and we'll get a 1N 4000. So just called a diode. I'm not sure exactly what kind of diode, but hopefully it's close enough. So we're going to get a function generator. And there's not a good way to set this in high Z in simulation, unfortunately. So we're setting the amplitude to 3 with no DC offset, sine wave, and we're injecting onto the diode, and we're returning to the resistor. And on one scope, we're looking at the input. So this is just going directly to the same net as the function generator. And then the ground, of course, needs to be ground. And then we'll set the time scale. So 1 divided by 60, it's about 10 milliseconds. So we'll just make it 20 milliseconds per division, maybe. We'll copy that scope over here and we'll plot the voltage across the resistor, just like we did here, right? So here's the input voltage in green, the output voltage, without this capacitor is what we're looking at. It's just that. So if we run this, you can see our halfway rectified signal. Pretty cool. So I think So we're using the data sheet just to find the maximum forward voltage drop. So if we open up this data sheet, um, assuming that it opens up, this parameter right here, VF, is our forward voltage drop, and there's an upper bound of 1.1 volts there. Um, so I think it might talk about that explicitly here. So here's the forward voltage characteristic, VF, and the, you know, condition that it needs to meet. And then I guess the last thing that we were doing is to use a multimeter to measure the voltage, right? So you would just place that in parallel with the resistor there. And I don't know what kind of multimeter this is, either AC volts or DC volts, but let's see. So 210 millivolts. That doesn't seem very reasonable, which leads me to believe that this is measuring DC voltage, right? Because if we're measuring AC voltage, it would at least recognize that we've got, you know, zero point 0.2, zero point 0.4, zero point 0.6, zero point 0.8, zero point 0.9, pretty close to 1 volt appearing there. And if you take the, RMS of that over a period of 1 divided by 60, then it should be a little bit more than 210 millivolts, I think. So that's just one thing to keep in mind there. And so, of course, which one seems reasonable when you're measuring this kind of signal? This doesn't look like a very good DC voltage, so you would probably want to use some kind of AC voltage measurement when looking at that. So hopefully that was helpful. I know I didn't get to go over how to use the specific lab equipment in the lab, but that's why you guys have access to the user manuals now, assuming that you did the first part up here. And after getting a little bit of exposure to it I guess yesterday, you should feel a little bit more comfortable, right? The more you use it, the more familiar you'll get with it. So thanks for tuning in. I'll see you guys next time.